Very particular.
Okay,
That's
time to
what I
get going.
was thinking.
I just got to figure out what we're going to do. So did you all read your email today?
Yes.
So you got my message? With the picture?
Yes. Yes.
Just wanted to mention one thing. Well, I probably mentioned more than one thing, but about the articles and one particular photograph. The only reason I want to emphasize it is because it is a historic photograph made with a focal plane shutter, and essentially it emphasizes what we call now visually the rolling shutter effect. And just like there are prominent people in art and science, there are some outstanding contributions that people have made that may be more technically oriented than any of that. Although in this particular case, the photograph is recognized both as a technical problem, so to speak, and our artistic contribution to the history of photography. So before I even put anything on the board, maybe one of you can tell me, did I try ESD on you last week?
Yes.
Yeah? Okay. Well, I'm thinking about the photographer's name. So if I connect with you, blurt it out. Or raise your hand. Who is it? It's not working. I'm thinking real hard. Damn. Well, fail again. Oops. I think I might have mentioned it last week, at least the photographer, if not the photograph. The photograph, it's kind of weird. It was made with a large format camera, probably in the 20s, and it shows a car with a wheel that's like this, and it's got a driver in here and people in here, and then there's telephone poles and people standing in the background. They're all kind of crooked. Anybody remember seeing this ever? Well, it's in the, for whatever that's worth, it's in the collection of the Museum of Modern Art as an iconic piece that depicts speed and whatever other attributes you want to attach to it. But Lartigue made this, I think, when he was fairly young, and the debate goes on over the years as to why did this happen. The camera that was used was one of those that I showed you last week, although it might have been a different manufacturer, but the idea was the same. In the camera, there's a curtain that has a slot in it, an umbrella, and he probably used the finest one that he had. Okay, and that slot, when he released the shutter, was traveling downwards in the camera. Now he was trying to keep up with the car, and if he had, in that case, he wouldn't have gotten this wheel like that. It would have appeared round. Now the spokes would have been distorted, but the wheel would have turned out round. The problem was that he didn't quite match the speed of the car, but he panned quite steadily, and you can tell that he panned steadily because the background images, the telephone poles or whatever they're on the back, they're nice and straight, and they're tilted. One other thing I should mention about this is, you can easily get confused as to what that result is, happens or occurs, based on the performance of the shutter. The thing to realize, if you're so interested, is the fact that in the camera the shutter is moving down, but if you translate that to the scene, okay, what's in front of the camera, that slot is actually moving from bottom to top. Because the image in the camera is upside down, reverse left to right, right? Now you can imagine the difficulty that Lartigue must have had one he used on one of the cameras. I think I collapsed it. It had a tube that comes up like this, and you look into it. Well, there, the image is reversed left to right. It's right side up. But in order to pan with the car in the viewfinder or on the ground glass is moving from right to left. But out there, it's moving from left to right. So you're going to pan this way while watching a car going this way. Probably very difficult to do. And that's probably one of the reasons that it didn't quite make it. The other one is that the car was probably quite close to him. If you look at the photographs, you see, much of it is cut off. He was probably maybe 10, 15 feet away from a car. So what happens is that the wheel, at the time that the slot was here, the wheel was here, nice and round. But by the time the slot got to the top of the wheel had moved, so then it was here. And that is what caused that oval shape to appear for the wheel. Now it's interesting that it's Lartigue's photograph that kind of made it into history books. Because there were a lot of other photographs that also showed the oval wheel that photographers had done, had made at racetracks. And none of them seem to have acquired the kind of stature in the art world as his did. I'm not sure why. In fact, he tried to duplicate this, and he tried to do it under controlled conditions and so on. And he must have, spent a significant amount of time trying to improve on it. But this often happens in the art world. The first thing that you made, even though it wasn't perfect, that one was the one that got picked up. And the other ones kind of went by the wayside. So, in any case, any time that you kind of analyze what the image might look like, you want to keep in mind what the interaction is between either the moving slot of a focal plane shutter or the rolling shutter in a digital camera. In the photograph of that cowgirl on the horse, what was the clue that a rolling shutter was used? Anybody?
Telephone poles in the back were.
Very good, except there were no telephone poles. Or were there?
Yeah, there were. Well, there were wood poles.
There
you
were
couldn't
poles.
tell.
Yes, you're right. There was a fence. Right, the fence. You say, oh, the fence is kind of tilted. I don't think so. Those are right. There are right angles to the ground now. But if you look closely, the effect is very slight. But it's there, and you'd say, oh. And that was done with a, what you might call an almost respectable camera, a Canon 5D. And so you probably will see the rolling shutter effect in particular, obviously in the digital work, on a more regular basis than the effect was visible maybe in the film world. Or, of course, with cameras that use a global shutter. Before going on, I also I wanted to I don't want to quote Martin Luther King, but I had a dream, and the dream was that I got kind of worried about my presentation having to do with keeping the exposure time constant, the aperture constant, as you ran that little test with the turntable. I think I made kind of a hodgepodge attempt last time to clarify as to why you might want to do that. And I forgot one thing. And that's what, and as I was doing it, I said, well, there's something wrong with my presentation here. I couldn't put my finger on it. So I kind of sloughed it off. I figured, well, nobody knows what I'm talking about anyway, so what's the difference? But I feel bad about that, okay? So I think part of the introduction was okay, and it had to do with the characteristic curve, and I like the film characteristic curves, but it would be the same with the digital one, it doesn't matter. So you go up like this, and you're kind of familiar with this. You get highlights and shadow, and you get so many stops in between. I think we we figured out that if you, I'm not sure I mentioned it this way, but if you make an average, or if you make a, particularly if you make a, you don't know what this is? Yeah, well, they're getting out of use somewhat. How about the meter? And they can be used in a couple of different modes, right? This mode, and what's that? Reflected mode, and this? Incident mode. And if I take this meter and I aim it at this thing, in that case, the two readings, incident and reflected, will be the same. Okay. So an incident meter says, I don't care what the subject is, okay? So much light is falling on me, the aperture, shutter speed combination has to be such and such. And then what happens is that the highlights will leave a density on film like that. And if you, depending on how you set up the digital curve, you get a highlight over there. And you get a shadow over here. So I mentioned something about the moving mark, right? 2 degrees, and 200 degrees per second, and giving us an exposure time of roughly a hundredth of a second for the moving mark, right? I think what I didn't mention was what the exposure, or what the if you look at the subject, okay, we have this turntable, you know, and it's got the moving mark over here, but this part, the other part, is black, right? And this is white. So the white, if the turntable is standing still, and you make an incident meter reading, says this will reproduce over there, and the black should reproduce over here, right? Now, if you assume that you want a good exposure for the moving mark, in that case you need to know what the exposure time is. You'll say, well, you know, this might call for an aperture of f4 at a hundredth of a second. So you say, okay, well, suppose now that I take, I make an adjustment, and I go from a hundredth of a second. Let's see, I don't want to do that. Yeah, I do. And that is, you say, well, I'll go from a hundredth to 1 second. One. So you make the adjustments. You set up your system based on 125th. Okay, so that's F4. Then you go to here. 8, what's that?
11.
5, 8, 11, right. And then 4, come on. Level 16, I gotta double it, forget it. 22, 32, and 45, right? So at 1 second, you set your aperture, because you're adjusting the exposure time, you're adjusting the aperture at the same time. So, but at 1 second, okay, you'll be using an aperture of f45. But the mark is giving you an exposure time of a hundredth of a second, regardless. Okay? So it'll be way underexposed. It'll move from here to here, right? Now what about the disc itself? Well, suppose that you metered the disc ends up black. So you say, well, okay, what am I going to do? I'm going to now see what happens to the black. And oh, on the black side, that's there all the time, right? I mean, it just changes, right? But the black is there. So if you now say, well, I'll expose what? Now I'm trying to figure out why you'd expose at f4 in 1 second. You wouldn't do that. I ran up against a brick wall here, and I'm trying to work myself out of it. Sort of the connecting concept here is that this is black and this is white. This is moving and this is essentially standing still. Now if this stands still, for a whole second, see how I'm going to work myself out of this. I can understand where the highlight will disappear at f45. What I want to do is I'm thinking, well, I'll solve the problem first, and I'll try to figure out how it all works. While the highlight drops, in another situation, what happens is that the shadows increase in density, unexpectedly. And in one case, this could be called signal, right? And this is your noise. In one case, the signal disappears in noise. In the other case, the noise overtakes the signal, because this starts to get darker and darker and darker. What I'm having difficulty with is conceptually figuring out why that's the case. Apparently I have no problem with adjusting the aperture and seeing, oh, okay, well, at 1 second I would choose f45, and if I do that, while the mark is giving me an exposure time of 125th as it's moving, at f45 it'll be underexposed by that many stops, and it makes sense. But now I want to overexpose the noise 7 stops. Yeah. When would that happen?
It might be moving slower than you thought.
Well, the black is staying there all the time. That's right. So that's kind of the crux of the matter. Is the mark is not there all the time. It's there only for 1/100th of a second. But the black is there all the time. So
you're effectively overlaying white on black at a constant rate. So, but the point is that the black doesn't matter, because even if you overexpose it, you have to overexpose it by so much that you lose the entire image, in which case you need to just readjust your
well, that's true, but actually, yeah, I think we're in the same wavelength here. What's happening is noise is building up, and if noise builds up, in that case you lose signal. Eventually. Now, if you have an extreme situation, okay, in that case, in one case you would lose the signal completely in the shadows. In the other case, you'd overexpose and have nothing but
white.
But white, because the black is not. If it were a black hole, you'd have no problem, right? But it's not a black hole. You know, anything which is black around here, you know, that thing, it probably reflects 1% of the light. And 1%, but you do it 1,000 times, you know, it starts to add up. And but I'm not totally satisfied with my, you know, I was so gung-ho about this, and then I got this far, and I was saying, well, okay, what's happening? how do I reverse this? Because as that comes down, even this, huh. I wonder if you expose the black for 1 second, even if it's at f45. Or whatever. Is the noise going to build up?
You have less signal coming in because of the,
Because of the smaller aperture.
Right. So theoretically, you'd have the same exposure as the 1/25th at f4, but with the white piece moving, it would disappear because you're as
And
the
what
white
about
piece.
the black? We're concerned about the black now.
I think the black would look pretty much the same.
I mean, the records are fairly shiny. I mean, there was a lot of straight line.
Yeah, let's not even worry about the shiny, okay? Let's worry about the principle is the black isn't totally black.
Right.
So let's say it's a 10% black. What happens if you overexpose it?
It gets slightly.
It's get lighter and lighter and lighter. So I'm trying to find out where in this relationship is there such a situation. Let's not worry about what the real record was. Let's worry about a theoretical even black that stays there for a whole second. But okay, so you're dropping the white. And now, which would be the natural thing to do, so that would just move everything that way. But how do I make the black go up? Well, the only way would be if I use F4 at 1 second, right? If I did that, yeah, the shadows would move up there. Okay. The question is, well, maybe that's the idea here, that if you happen to choose this aperture for that exposure time, and then you keep that constant as you go down, you don't change it. Yeah, now your shadows are going to build up, and if you do change, now your highlights drop down. So the whole point, and I think this is mentioned in the little article that I've either passed out, I think, or I pointed you to it, that you should choose something in between, and you just stick there, and then you'll build up density in the shadows, okay, at some point, and you'll drop some density in your highlights, but the chances of successfully recording your data, which is you're interested in, are better than if you have to deal with very little information in the shadow side or an awful lot of it up there where everything gets mixed up.
The way I see it is, as long as you keep either the signal off of the toe or the noise off the shoulder, then as long as you stay in that straight line portion, then it doesn't really matter what the exposure is.
True. That's right. So, but the thing is, you can easily go off if you start to get a little too close here, or if you get a little too close there. Right. So, 3 stops down, 3 stops up, something in between. So there is some logic to it, and I think that's the more important part of it. In a situation, in a technical situation, you want to gather information. You don't care if it's theoretically. You don't care if it's noisy. You don't care if it's out of focus. You don't care about an awful lot of things. you want to make sure that you have data. This is sort of an aside, okay, what I'm mentioning now. And it has to do with infrared photography. And since you can't see it, you don't know where it is, some people want to say, well, what is a proper exposure to use for infrared photography? Make it so that you can see something. Because if there isn't any, okay, if there isn't any, or if the level is very low, in that case, and you don't get a response, that doesn't help you. You say, oh, well, you know, I didn't record anything. That might be the proper exposure because there isn't anything there. But wouldn't it be disappointing to get your digital file or whatever it is with nothing on it? And you know, but you don't know whether there was something there. So you want to force it so you get something, even though it's incorrect, right? Everything for data. Yeah, it's kind of a philosophical approach. It doesn't help you to say, I don't want to repeat myself, so I won't. Okay. What else was there? It was a nice shot of the girl and the horse, wasn't it? Whether you saw it. Okay. I think it's maybe time to go on. Oh, so here comes the perennial question, whatever it is. Are there any questions? Given that there are no questions, I assume that everything we've covered so far, in every minute detail, and everything that's on those handouts that you see, is completely understood. Because otherwise you'd have a question, right? And the audience says, you're right. Yeah, it's on the record. How many of you got to see the YouTube from last week? It's kind of boring, wasn't it? Anyway, it's there, and I'll put the second part from last week on there. I just didn't have time to do it, and I'll do this. I'm not sure it's of any use, but maybe it is. So, let's see. Well, it seems like we're probably going to get done early today. I think I'll introduce this topic, which is related to what we're going to do tomorrow, by mentioning William Tell. You all know what is associated with William Tell? Anybody?
Besides the overture?
The what? Oh, besides the overture, right?
Shooting the apple.
Oh, the apple, shooting the apple. Yeah, okay. And who else was kind of connected with apples?
Johnny Appleseed.
I think he's going for a
All right, we're getting a creative response over here. All right, that's good. I like that. Yeah, Newton. Right? Newton, what was the thing about Newton? Was he standing under a tree and got hit by an apple? Is that it? Is that what legend has it?
I don't believe it.
I don't either. I think it was a lemon tree. It doesn't matter, but the legend, okay, has it that as a result of maybe thinking about things, Newton got involved in trying to figure out how things work, and particularly it was connected with gravity, gravitation, and motion of, I shouldn't say this. I'll get crucified for it. No, I won't.
Now we kind of need to know what it was.
Okay, the motion of heavenly bodies. Anyway, but that's it, you know. How did the planets move? How do other things move? And he wasn't the only one. There was an awful lot of, I mean, there's a lot of science now, don't get me wrong. But at the time of Newton and others in that era, maybe 1700s and so on, you know, that's before computers. You had to do everything by hand. Galileo, you know, but you could go back to the Greeks even. They did amazing, amazing things just by thinking. And so there is Newton. And anybody remember any of Newton's laws? One.
F equals on
What's that? F?
Yep.
Big F?
Sure.
Is equal to?
Little a.
M A. And this means, this is what? F stands for what?
Force.
Force. And this is mass. And that's acceleration. Okay. Any others?
And object in motions will stay in motion.
Stay in motion.
Unless I act upon an unequal force trend.
Right, sorry, you missed that one.
And for every
Reaction.
action there is an equal and opposite reaction. Right? Yeah. I wonder how long it took them to figure that out. So, but there is an effect, or an event. I'm not sure what you call it. This thing does something predictable, right, as it falls. Newton figured it out, what it is. What's the thing that drives this? Gravity. And what does this thing do as it falls? Accelerates. So gravity and acceleration has something to do with the rate of motion of this pen as it falls. Right? There was somebody else who got picked on for something else having to do with objects falling. Anybody know who it is? The what? Chicken Little. Or Humpty Dumpty. Yeah, no. A motion experiment. I think it was a pretty, at least it was a statement. I'm not sure how the experiment worked, but there was somebody who I think eventually got sort of banished or crucified by the Catholic Church for being a heretic. And he did stuff with astronomy, but he also worked was in the vicinity of a famous building in Italy.
Galileo.
Yeah. Now what did he say?
Well, he said all objects fall at the same rate.
Right. Now he didn't try with a feather and a steel ball, right?
That's true.
But I think he went further. He realized that the reason that a feather and a steel ball wouldn't fall at the same rate is because of
Air resistance.
air resistance. Right. I said, well, if there was no air, they fall at the same rate. Now he couldn't actually prove that, right? But he envisioned it. Yeah. Smart cookie. I'm not even sure they knew at the time that there was such a thing as a vacuum. Well, actually, you know that there is no such thing. There isn't a vacuum. It depends on how picky you get. Right? One molecule in a bazillion cubic yards. Well, that's not nothing, right? It's just very small. So, but I think at the time, they weren't even thinking about that. But nevertheless, we're going to get back to Newton here because of this. So our objective this week is going to be to use the calibration techniques that we use to calibrate the shutters, to then use the shutters to make measurements. Okay, so we have, what we had done is calibrated against the standard, and now we're going to, now we say, well, our cameras are now essentially the same as the standard because we know what they are. And now we're going to use the cameras to measure something else. We're going to essentially prove or disprove Newton. And what are we going to do? Let's see. Oh, that's actually not bad. I can really only see one out of one eye. So it's kind of weird trying to reach for things and not catching them. But I think next month I'll be able to see our both. Okay. So what we're going to do is to take we're going to make life easy on ourselves and photograph a couple of different types of falling objects. Now, one of them is going to be a steel ball, and this is going to fall. And okay, I'll be the first to admit I cannot derive Newton's the relationship that Newton established for us to be able to determine what the rate of motion of this steel ball is. But I will tell you what it is, and we will work with it. I'll do that later, but first of all, what we're going to do is to just look at this falling steel ball. We'll realize that, and we'll take a picture of this, camera or whatever, and we'll look at this field right there. And for the sake of argument, we'll say, okay, we operate, and we make sure that the shutter is operating in a direction perpendicular to the travel direction of the ball, right? Because if it travels with or against, in that case, our results are going to be influenced by that. So the shutter is going to, across. This is going down, and at some point or another, the shutter of the camera is going to open. Right? There's a good friend of mine from MIT who wrote an article about blur is beautiful. A sharp picture is okay, but it doesn't tell you much. How about blur? It tells you something. So the exposure of that ball is right here. And then we choose an exposure time, kind of longish, so that at some point when the ball is over here, and the image is over here, then the shutter closes. So what we get in as a record is something like this. You agree?
Yes.
Now, our gut feeling is that if we could figure, and if we knew what that distance was, we could determine what the average speed of the ball was. So we say, okay, what is this? I don't know. If you're close, it's something. If you're far, it's something else. So in order to be able to measure, we can actually draw this out to the subject itself, right? Subject is just going to be ball there and ball there, but we know that it's caused that blur. So we want to measure this here. How do you think we would do that?
Oh, I'm sorry, what was the question?
Oh, you're scratching your head. Just kidding. The way you do most of the time, and that is you introduce a scale. Put a ruler right here. Now, you have to be careful while you put that ruler, right? You want to put it in the same plane as the steel ball is, right? Now there's another way to do this, but I'll mention it maybe in a second. So you put a ruler next to it, okay, and then you can say, okay, well the top of this is over here, the bottom is over here, distance between here is 1 foot. Okay. Now you can start to say, well, velocity is equal to change in distance divided by change in time, right? We know what the change in distance was, 1 foot. And we say, okay, well what exposure time would we use in the camera? Well, about a tenth of a second. In that case now this becomes 10 feet per second, right? Now I only say that this is, I mentioned this is an average speed, and I think that's always true. But the problem is that the speed of this steel ball is changing, right? It's accelerating. Now, just as for the sake of argument, I mentioned the fact that you introduce a scale. That's the right thing to do. But what's another way to figure out how far that ball moved?
Object and the image distance with magnification.
Yep, that's one. That's another hard way. What's another? You measure how wide that ball was. Let's say it's 1 inch. 1 inch, right? You have a built-in scale. It's your subject. And you measure the height of this in terms of its width. And the width you know, right? So sometimes you get lucky because you know what a dimension of the subject is. And then you measure the subject in terms of what you already know. And you don't have to include the scale. The scale is included in the photograph. Those are neat situations when you can do that. Because putting a scale in here really doesn't, I mean, you gotta be pretty lucky for this or anything else to be in the same plane. Now some of you are in biomed, okay, and you do like they call it gross specimen photography. Now I've seen this a lot. Here's a table, you put a gross specimen on here, and you put your scale down here. And then you measure something over here. Uh-oh, that doesn't work. Right, it's I mean, in your camera's over here. It doesn't work. This is closer than that is. It's just an aside. But scale is a very important part of making measurements. In aerial photography and so on, this also comes to play. You gotta know the distance. If the distance changes, your magnification changes, and your measurements go out the window. So, but in our case, we can state that the average velocity is whatever it is, 10 feet per second. However, over here it might have been 5, over here it could have been 20. That's the problem with average speeds. So what we want to do is to maybe compromise. We know that the best result would be if we could make the blur very small, right? Like that big. Essentially meaning that the instantaneous speed here and here would differ by very, here and here would differ by very little. And this is really what calculus lets you do, right? Yeah. Because it deals with infinitesimals, infinitesimal changes over time, for example. So you could describe the performance of this as long as you get individual instantaneous speeds, and then generate a curve based on inputting it into a calculus for this. But see, unfortunately, it's beyond me. I got a letter not too long ago from a graduate who's working in Switzerland in a colored, high-level computing system. And she was complaining to me that she doesn't have a social life. Because anytime she goes for coffee, or they have a coffee break, all her colleagues are talking about high-level math. And they're having great fun with it. And she can't participate. I was feeling kind of left out. Well, don't feel left out. You have other things that you contribute to this, to the effort. You got to work it out. Drink more water. I don't know. But it happens, and the truth is, it happens to me. You know, I go over where this fellow comes from, and they're talking over here, and I'm down here some. But that's okay. I must say that I did pay my dues. I did do calculus for several variables and differential equations and so on. But unless you use it every day, you just fall out of it. But math is okay. It's good for you. So anyway, Newton figured this out. And he came up with a relationship that allows you to determine how fast things are moving as a result of gravity pulling on them and the distance that they have moved from rest. So, and that is, the velocity is equal to the square root of 2 times AS. So, there's our friend acceleration. S is the distance that the object has fallen. And 2 is just a 2. And the square root of that is how fast anything is moving. So as part of the project, the teams or however you're handling it, you should generate a graph, because you're going to say, well, this is what Newton says, and this is what we find. So I can kind of walk you through the first, or an instance or two, of how Newton would go around to put points on a graph. We would have a dependent variable, right? And usually those were down here. Is that right? And we have an independent one, which goes over here. So whatever goes here is a result of what's down here, right? So this is S, and this is V, right? Now, the numbers could be in inches, it could be in feet, it doesn't really matter as long as acceleration. I guess you have it all in the same units. So the easy thing to do would be to say, well, how fast, if something drops 1 foot, at the end of 1 foot, how fast is it going? Okay, 1 foot. So we take that and we plug that one in. What do we get? 2 times 32, oh, 32 feet per second, is that right? And S is D, which is 1 foot. So anyway, it ends up to be, what, that's 64? And take the square root of that, what's that, 8? It turns out to be 8 feet per second, so something doesn't look right. Let me, I just have a gut feeling, so I'm going to test it out. Help me out. Started out like this. B squared is equal to 2AS. Now I did I did that. And did I do the right thing? Yeah?
That first equation's right.
If this is right,
Yeah.
then this is the same thing. 1 foot is about like that, right? Well, I'll take Newton's word for it. Just seems awfully fast, doesn't it? So, let's take 2 feet. So anyway, I always have, how do we do this? Maybe 5, 10, 15, 20, 25, 30, 35, 40. Okay. So at 1 foot, we're already over here. Right? So well, let's do 2. And what happens then? So everything, this goes to a 2, so that this is 64, 128, right? And the square root of 128 is what? That'd be a nice number. I don't know. Anybody can do it for me? It's for a number that multiplied. Well, it would be 10, 11. What?
8 root 2. 8 root 2. It's not that
Yeah.
pretty.
I got you. I got you.
It's not a pretty number.
It's not a pretty number.
So
11 point something.
11, 12 or something like that. Because root 2 is like 1.5, so.
11.3.
Yeah.
Something there. We do it with 4. No, let's do 3. So 3 times 2 is 6 times 32.
8 root 3.
What is it? 64 times 3
Yeah.
is what?
It's just 8 times root 3. It's still not nice. 4, it's nice again, but
Okay, so but what is it?
Let's see.
Roughly what?
Root 3 is like 1.7.
Times 8?
Yeah. And so that's like 2 times 8, that's like 15. 14, 15-ish.
yeah,
there.
close to 14.
And then 4 is
4 is 16.
I guess maybe
Okay.
15, 14-ish.
anyway, this starts to keep going like that, I imagine. But at some point, you know, if you start to do it in inches, now there's going to be a pretty sharp cutoff point. So you draw essentially based on this. He first says, first step is, what does Newton say? And you generate the Newton graph. Now we're going to check it at 1, 2, 3, 4, 5, and 6 feet. And at this point, we're going to take a break for 5 minutes, and then we'll reconvene, all right?